And main focus for the last two lectures on recycling and both e-waste as well as other the batteries. So I think now the way we discussed yesterday, when we talk about advances in mineral processing, particularly for the beneficiation part, I will continue on it. But otherwise, some of the operations that are essentially needed even for recycling material is basically you need to still do the size reduction that is needed for the exact liberation target. And followed by, you also need to go for further enhancement of the feed that is suitable for your downstream process of either hydrometallurgical and or followed by directly if you go for the pyro, that preparation you have to do it using the physical methods. And these physical methods are plenty, I mean, ranging from crushing, grinding, also to the extent separation of them. So there are, I think, about modern, I would say, in the last 5 to 10 years, there are about certain new developments in terms of the reference books are available. I think this is one of them, that mineral processing and extractive metallurgy, 100 years of innovation that happened in the in the area of mineral processing and extract metallurgy. So this is one very nice book. If you want to really look at it, the concepts, details of this in a way to go and refer, you can use it. And also there are two books released 2021 during just COVID time, mid-COVID time, called SME Handbook on, again, mineral processing and extractive metallurgy, 2 volumes. Those are also available in the library, I guess, and you can also subscribe them electronically if you have some reference to use it. So most of these, whatever we talk about it, not specific to targeted to critical minerals, but mineral processing and extractive metallurgy. And so today, if we talk about critical minerals, as we have seen yesterday, that now the same technologies, you can still adopt it. But then what you need is actually refining or intensify the process that you can actually adopt for your critical minerals. So that means now we are not saying that we close the door for innovation, right? It is still there. But then if you ask somebody saying that, I want to produce in 1 year, now what you need to do is use the existing in a way where meritoriously you can actually fine tune to get your required product. So that is the bottom line. Then we need to understand that we are not going to do differently for compared to conventional minerals to critical minerals, especially your pre-treatment and even to the extent hydrometallurgical route that we go on it. So if I look at it, this is what the methods for critical minerals. These are the 4 major areas that we need to realize importance for the critical minerals. One is starting from your feed preparation. You are starting from feed preparation to final refining, where you have to have a specific advantages that are existing to adopt it. So feed preparation and liberation point of view, we have seen what to do. Even for recycling also, your feed preparation is a definite attempt needed for you. Otherwise, you cannot process directly. So that's where we have mostly looked at, but I think I can recap in the next slide what are those, how we have attempted. Now, the next is advanced physical separation. This is the beneficiation route. So in this, not all the physical beneficiation methods are useful, but depends on the case. Like if you talk about a primary votes, obviously you have to go through the same routine. There's no exception for it. But only thing is the way that you need to grind and get liberation advantage, probably you need to go for very finer sizes. And the problem comes is the moment you go with the finer sizes, your separation is going to be very, very challenging. So, and that's why traditionally industry, they don't easily process below 45 or 53 micron material, and they keep them as a tailings, and then they preserve them as a tailings dams. And because most of the process are wet, then you need to recycle the process water for your plant using thickener and all of that. So you have one set of tailing dams, And before you drop your tailings, you can also recover your process water back using thickeners. So this is a conventional technology. Anyway, we need to have it any wet process industry that we use in mineral. But then the moment you go with the finer sizes, what are the available ready-made technologies that we have? How we can use it? For example, gold, right? If we go and look at it, you might have seen many movies, right? One of the movie that I can recall is um, the Blood Diamond. Okay, if you recall one of the movie, African, I think Congo, or I think it's in Congo, right? Yeah. So conventional people, they use kind of a shallow tray to do all that, but then the smart guy, he brings up the advanced gravity separator, and he started processing, and he hires the labor to do all that job, and he faces a lot of other issues. But if you look at the technology that he brought in, basically it's actually nothing but it's a high higher advanced centrifugal separator, and which can be used even for critical minerals if you have that level of particular high density material compared to the other mineral. So those things we can look at it. The further, some of the majority of the materials, especially if you have a sulfide contamination with it, you have to go with the flotation. And froth flotation, we know generally the principle, but the problem with the froth flotation is there is a difficulty separating the particle below 50 micron. And then how do we actually separate? Because one side you are saying we want to go for very ultrafine grinding, and when you generate such fine particle, if the flotation is going to not going to respond, then there is a problem. So how do we actually look at next generation flotation of the fines and ultrafines? So that's an important task we should observe. And then the last part is a process identification, control, and water lean flow sheets. So that means now the more the finer size particle, the processing also becomes challenging in terms of water recovery and process water for your recycling. Now, can we think of the dry beneficiation, and can we think of certain way where we actually use certain chemical aids to minimize the moisture content in the product and all of that? I think those are essential part, but we cannot ignore it. Okay. So going through the first part where feed preparation and liberation, I think most of it we looked at, especially the grinding part. HPGR we have seen, probably they are the best in terms of the efficiency point of view for mid-range particle, starting from, we can look at it coarser particles, replacing secondary, tertiary, and also primary grinding straight away. And energy efficient, probably in India we haven't started adopting them, it is still in the research, but I think most of the countries already started utilizing for energy point of view to use it. The second part, stirred mill, isomill, and vertical mill. This is for fine particles. I think again we looked at other day saying that we can go for 20 micron range of liberation for refractory oxide systems, particularly if you have rare earths in fly ash, vanadium, titanium, and magnetite slimes, and to the extent all the secondary resources. If you suspect that there is some possibility of liberation, you can able to enhance it. You can attempt to do it. Third is for all of these materials, once you grind it to the final sizes, now as simple thumb rule, if a particle, let's say I have about a 100 micron particle, if I leave 100 micron particle, typically how long in 1 meter column, how long it will take to settle down? Guess? No. If you leave 1 meter column, one meter long water column and 100 micron, you just leave there, it actually takes 1 year by its alone to come. So what you need is actually the processing time to be minimized. So for that matter, we go additional treatment, like instead of single particle you allow, can we make particle aggregate so that the particle size can be enhanced? So this is where we start using in a thickener designs. Most of the designs we talk about how we can actually enhance the particle aggregations using flocculants. The flocculants actually essentially aids for, especially when the particle is about 10 micron, even above, they can target to do that, so that once the particle is big enough, then it starts influencing by the gravity. So then we need that kind of interventions where probably further liberation is possible with the microwave treatment, where I can able to do the surface actuation for separations through flotation, and thermo roasting, mechanochemical activation, basically even ultrasonic treatment that you can able to do. So those things would actually work on either to weaken the gang or to enhance your the valuable mineral for leaching or flotation. So those are again essentially needed for us. Then the last part is the desliming and slimes management. So particularly when you deal about the tailings, let's say a lot of critical minerals are there with the tailings. Now, if somebody says, okay, now we need to target to generate the valuable from the tailings. But I think the first principle we should look at it, how do I reject most of the gang in the beginning? So that is where the desliming and slimes management you need to do it, so that 30 to 50% of the material you can actually discard, which you don't have to process through that system of refinement. I think that saves a lot of money in terms of economics point of view when you look at it. So we need to look at those as a feed preparation and also liberation aspects point of view. Now next is the physical separations. So on physical separations, so I have the notes which I can circulate later on fundamentals how they work on it. But let's not go into the details of how the physical separation works. But if you look at it, there are about 5 classes that we are keeping here for your reference, where you can go back and refer that. The first one is sensor-based sorting. So now, if the particles are quite big, you can actually adopt it as a what do you call sorting itself. So in some particle, if they exhibit the dielectric properties, probably if the particles are big enough, you can able to do it. So that is where the X-ray based techniques and also the PGNA and also nuclear based sensing, you can able to do early rejection of the gang, ideal for very vein style copper, cobalt, nickel, and also tin, tungsten, and also rare earths bearing hard rocks for the recycling feed. So these are, you can actually make it as a sorting based separation, which can able to get your maximum if you are talking about a primary ore point of view. If you go like for example in monazite, some of the typical rocks you can also easily identify that rich in the the certain fraction of the monazite and also rate. So they differentiate it based on color. You can also have properties, and also you can go with certain other nature where the nuclear sensing also can be able to detect it. So those techniques are also evolving fast, and I think for primary ores point of view, if we want to adopt them for critical minerals, probably well advancedly available where we can adopt them. The second part is a gravity separation. So the gravity, there are about all of this where we talk about a density based separation. So that means now you need to identify the density fine separation, because the moment you grind or you crush to finer size particle, most of the dense medium separation we go for coarser particle. But then in case of the heavy density, you can still do the fine dense medium separation. For example, lithium. If you are getting a lepidolite as a primary source, then what you can need is a hard rock. And then for hard rock, one way is you can able to do the dense medium based separation, and followed by again you can subject for flotation and other processes based on what is the enrichment that you want to do. So the efficient dense medium separation definitely is a one scope that we can adopt for critical minerals, provided they are coming from primary. And then it's very difficult to go for very fine particle. Let's say if the particle size is below 300 micron, obviously they may not work effectively because you are adopting the centrifugal acceleration, even though they may not able to get separated. Rather, you can use as a advanced classifiers to do that job, which we have at the bottom anyway. Now, apart from that, if the particle size is mid-range, now high gravity spirals are evolving better and better. Fine as well as high density particles, if you have it together, and if there is a reasonable density difference between them, you can able to separate. So this is again another scope for intermediate size particle before you go into flotation, that you can adopt it. And some particles anyway they may not able to respond for the flotation, then you need to do entire stuff through conventional gravity separation. So then you can go for high spiral gravity with the multiple series method to enhance further and further. For example, if you look at monazite, which is again a nuclear mineral, but the monazite, the way we process it completely by spiral circuit, and then at the end whatever you get as monazite rich, Then if you process it subsequently, you can also get our rates as a byproduct through your hydropyrometallurgical route. So then going on to further very fine particles, we have again some of them already well established. For example, Falcon and Nelson separators, and also multigravity is there, but I think it is still restricted to R&D labs. But Kelsey as well as a Falcon Nelson, you can target about a 1 millimeter to 10 micron range, and these are the various mineral that you can able to do it related to critical metals. So again, what is this Falcon, Nelson, and Kelsey separators? Is nothing but high centrifugal separators. And high centrifugal separator can able to go and make your particles effectively up to 10 micron to get separated, but only the constraint is actual capacity. So then, and also they are expensive, but I think when you are getting, for example, gold, typically the Nelson Falcon, they use a lot. And the reason that they use them, because you want to capture gold particle which are up to till 10 micron. You don't want to lose them. So obviously, it's you have a the profit that is still feasible despite whatever the process is limited in terms of the capacity. But then it makes you to go with the large capacities if you have a parallel circuits that you can adopt it. So that is where Falcon Nelson separators still it's a good choice if the particles having a sufficient density difference between the gang mineral, and you can able to adopt them. Then the another gravity separators are magnetic and high gradient separators. I think these are pretty much Salon and then WIMS are actually having a very high magnetic susceptibility range separation. So you can go for superconducting HGMs also for weak magnetic materials that are there. So you can go for ilmenite, garnet, and also rare earths bearing monazite and xenotime association. So then again we are targeting where the particles have a response for the magnetic susceptibility, you can able to adopt for finer particle. All you need is, if in magnetic separations, you have a limitation if the size is too small. But then what if you adopt the high magnetic intensity generated within the system, then you can able to capture to the extent that is possible. So that those are again available for critical minerals. And the electrostatic and triboelectric separators, particularly for dry processing, are sensible. And for example, STET type belt separators, where they can able to use carbonate silicate or quartz feldspar carbon to ash splits, powerful for cold flash too, to get your ray rates. So again, people have attempted to concentrate the ray rates before we subject for the hydro processes. So that is the and then the advanced classification also needed, because wherever you attempt your grinding, or where if the dense medium separation not able to feasible for among the narrow size narrow density range particle, then you can use these things like reflex classifier. Again, this is one of the latest novelty that is there in the last 50 years time, I would say 40 years time. And now they are there in the industry capacity range where you can go and utilize it. And teeter bed, nothing but again, you try and make particles in the fluidizing condition and get the particles of a density based, where higher density you can tap it based on what is a bed density that you maintain. So if you maintain the lower bed density, now you can really enrich the heavier, lighter part, moderate density particle, but lighter one goes as a rejects that you can go on. Hindered settling columns also there, but I think sharp separations is very difficult with the hindered settling columns. But I think some of them are quite good if we operate at a dilute concentrations that are possible. And also we can use advanced classification using novel hydrocyclone based on your process that you want to target for. And also efficient screens. So screens, I would not recommend if the particle size is like really below 50 micron, but otherwise above 50, there are quite decent screens that are efficiently can able to separate them. So these are the advanced physical separations suitable for critical minerals. And we cannot generalize saying that we can use all of them. No, I think you need to pick and choose based on what are the characteristics of your feedstock that you are targeting to do it. Next is the next gen flotation, especially when you go for very fine particle and ultra fine particle. Conventional flotation is very poor at responding. So then we need to do many things. In fact, after the gravity separation, the flotation is one of the oldest technology. I think more than century 100 15 years old technology evolving. And it's again, flotation is being believed, there are two versions of, acceptance for the flotation. So if you are a chemist and geologist, you feel that reagents are going to play a major role for me as a flotation. But if you are engineer by practicing, then you would say my hydrodynamics for the particle and bubble would be a major controlling parameter, because what they say is, if the bubble is here and the particle is here, there is no way that the particle will get attached to the bubble, right? So what you need is, you need to bring them close enough so that you actually enable the surface forces for the particle to get attached on the bubble and stay stable way to rise up. So I think despite all of this, probably what we need to do is, we need to go with the united way, saying that yes, we need to bring the particle close to the bubbles. But now question is, what is the difficulty for the critical minerals having a fines and ultrafines for flotation to act upon? So the one is, let's say you take a mechanical flotation, right? You are actually inducing certain stirring to bring the particle close to the bubble. But in the process, what happens is, even if you stir the impeller based rotation for a fluid, now a particle of 10 micron, let's say for example, would not come closer to the bubble. Rather, what it does is, it follows the water path, because of 10 micron particles are actually very influenced by local turbulence. If I have a high eddies created near the impeller, my particle never comes to the bubble surface, but rather it actually moves along with the water and gets recirculated. Now, such fine particle, what you need is, probably big size bubble is not able to have enough contact, and you create a fine dispersed bubbles to do it. So that's what the fine flotation, that you go on targeting the finer size particle, but ensure your bubble is also fine enough to go and have an effective streamline. Like for example, if the 10 micron particle is moving along water, if you create again a bubble of a millimeter or less, it might also go with a similar manner. Then both will be in the similar path of the flow circulation, and there is a probability that you can able to enhance the flotation. And that's on a hydrodynamic point of view. But of course, chemically you can also enhance with respect to adopting certain reagents, which can able to minimize the disintegration of the bubbles to go and have a stability of the flow and bubbles. So that's where we look at it. Some of these designs are nothing but like column flotation, the column flotation and Jemison flotation, air spots, hydrocyclones. These are available, but I think air spots hydrocyclone is the latest one, still at the R&D exploration. And people have attempted, but I think specific to critical minerals yet to be tested. But otherwise, the columns, they can able to do Jemison, and also Jemison cell is again, it generates a microcell and Jemison cell, nothing but they generate the fine bubbles in the system. So that's advantage. So in case of column, why we are choosing the column over the mechanical cell, whereas Jemison and the microcell, we understand that there is a fine bubbles generation happening. But in case of column, it's not always a fine bubbles generation, but I think we are trying to minimize the turbulence at all. In column, what happens? You have a cylindrical section, and then when you have a cylindrical section, you don't have any stirring or induced turbulence. Rather, what you are trying to do is, you are actually making the particle and bubble to go in counter current fashion, so that there is no turbulence is being induced. But that's a concept. But I think if you go and look at the actual industrial column flotation that they are operating, of course, operators always are greedy to increase the throughput. So then they increase the flow rate, and then they also get some losses of it. But ideally, you should operate the column flotation not into complete turbulence, but I think laminar to transition region, so that the interaction of the bubble and particle is going to be in a homogeneous, but not into completely heterogeneous level. So that's a philosophy one need to adopt if you are adopting the column. Now, in case of Jemison and microcell, as I said, the generation of the bubbles itself very fine. Then they have a potential to go for the fine particle separations effectively compared to others. And then the latest trend that is coming across, I think a lot on the R&D mode right now, is a micro and nano bubble flotation. So here, the idea is, though the junction cell and micro cell, they generate the fine bubbles, the moment they come and have an interaction with the liquid that is coming, or the slurry that is coming, the bubble growth is happening. And they have only demonstrated in a way where, compared to conventional flotation, you have a better recovery. But then they could not able to prove completely, saying that the bubble growth can be arrested or not. So that is the reason. Now, if you want to have a, let's say, millimeter size bubble, I'm talking about a 1 millimeter or half a millimeter bubble. Whereas a conventional flotation, if you go and check it, they're about a 1 millimeter to 5 millimeter, or to the extent even coarser bubbles are there. But now Jemison and micro cells, they are generating the micron range bubbles. But the moment they go into the system, they are in the above millimeter range. And especially when they are reaching the top flow regime, where the actual input of the slurry comes, and they are actually bigger in the size. Now, the thumb rule is, if you want to limit your bubble size less than 1 millimeter, I think your initial size of the bubble should be very small, and that is where the micro size range bubbles as well as the nano bubble are being targeted at the laboratory level. I think nowadays nano bubble generation is quite possible, where you can able to target for the kinetics of the -20 micron for recovery effectively. So this is where we talk about the entire philosophy that we discussed yesterday, generating the ultrafine, utilizing the ultrafine grinders for generating the fines. Now separation is the way that is feasible, provided they can respond those particles for the flotation. And that means now we need to look at the characterization of them with respect to contact angle, hydrophobicity, and all of that, and whether they have the sulfide content or not. Because usually most of the particle having a sulfide content have a hydrophobicity behavior that you can able to do it, except coal. Coal has a different quality in a way where you go on. So then the next part is, as I said, first two are only hydrodynamic point of view, why they are good at it. But I think the reagent still you need a better way. So these are the third and fourth point, particularly targeting about the new reagents that you need to bring on. So reagents here, what you need is, see, for example, now we talk about a lot on a lithium, and if you are getting a lithium from primary resources, now you'll be going through again your combination process and also dense medium process. But through dense medium, you have a limitation to go up to 300 micron, maybe 250 micron, not below. Now, what you do below that size particles? Now, what you have to go for is flotation. Now, flotation is a other option for lithium to be again floated, enriched better before we go on to hydrometallurgical route. But then, if you look at that part, now the reagents for lithium flotation is still not clear. Okay, and the reason is the contaminants or a gang material that are associated with the lithium would be needed a special attention to design your reagents. So I think few places it's happening, and then they started utilizing based on the characteristics that are needed for your feed material. So these chemi-selective collectors, especially for phosphate and also rare earths in the carbonates, you can use it, and also hydroxymates for rare earths oxides, and also you have a nickel cobalt sulfides. If you have it gang combined with the gang complex gang, you can able to use these selective collectors. And selective collectors, again, these also need to be, because you are talking about a multi-metallic mineral. When you have multi-metallic mineral like chalcopyrite, for example, it has a copper, lead and zinc. Now usually what they do is three of them are valuable. You cannot just take one and throw other one. But then when you are floating, let's say, copper rich particle, now remaining zinc and lead rich particle, you have to suppress them not to respond for the flotation. So then your design of or selection of the reagents that you choose, frother and collector, should be carefully chosen such a way that only the activation of those copper rich particle in the first place will be selected, and then the remaining you have to use them as a suppressor or a depressors of it. But then the second stage, let's say I've done the copper flotation, now I move on to lead. Now in that process you have to again activate the lead-rich particle and suppress the remaining two, whatever the tailings that you received from the first target. Now, again, the second, and also these, not only the reagents that you select, your pH also plays a major role for flotation. So if you go to the basics, there's a lot more fundamentals that we need to understand. But otherwise, those slides I have with me, I can share you separately to go through. But otherwise, now in the second stage, you are targeting lead, but the remaining two components you have to deactivate and should not respond. And similarly, the final one. So that is how selective collectors you have to go when you have a multi-metallic components that are there with the system. So this is again a thumb rule that we go. But if we'll try and characterize a flotation behavior, so contact angle is a one measurement that indicates for a specific component whether it's a highly floatable or not. If not, you need to modify the surface such a way that you also add some of these reagents to do it. And preconditioning also is quite possible. Like for example, let's say we are dealing a project with one of the corporate industry to enhance the oxidized coal flotation, because oxidized coal is not highly floatable. But then when you have oxidized coal, then how do we modify the surface? So one way we try and attempt in a way that can we now subject for local hydrodynamic cavitation first, so that surface would get activated. That is one, like using ultrasonic treatment or so. Or can we also make a microwave treatment for the particles, so that not at high temperature but cold temperature, so that you can actually get a surface activation reasonably well for some time. And within that time frame, if you try and subject for flotation, probably you get a better yield and use it. So those conditions we can adopt as a combination of the collectors. Again, because the moment you modify the surface slightly, now let's not expect the same response we get it from the conventional reagents. Okay, and then you need to do and trial and error or even combination of the reagents, that how they work on it. And then we need again depressants and dispersants. Basically, when you go for multimetallic, these are essentially needed to control your required target of the component to be floated and adopted for the separations. The last one, bioflotation, which is emerging, where using bacteria or bioreagents, they can modify the surface chemistry for eco-selectivity. So this is again has been tested for chromite, iron-based separation for bioleaching. But flotation point of view for critical minerals still is ongoing research. And particularly some of the European countries, Norway and Sweden, they are trying to adopt this bioflotation for some of these critical elements, including the lithium and other components. But I think it is still at in laboratory range research, whereas other components they got better maturity for immediate adoption for critical minerals. And fourth one is the process intensification and control, where we can try for water lean technologies that are needed for developing the flow sheet. So the dry beneficiation, obviously it's attractive, but it is not quite feasible for all the type of critical mineral that we talk about. So even for conventional mineral itself, it's very difficult. Okay, and in fact, for coal, it's more than even 100 years we are working on the coal research. But then if you try and look at effective the commercial practice of the dry beneficiation is not there in India much. And whereas China, they have already adopted it for low-grade coals to do it. Yeah, so I think that's one area still Coal India is watching for to get a better off for commercial level. Pilot scale research is already done, like IMMT Bhubaneswar long back, using air dense medium separator. But I think further TRL 6 and above, they could not take forward. Basically, recoveries are quite low compared to the dense medium wet route and flotation. So otherwise, you can actually use with respect to combination. For example, HPGR anyway is quite good in terms of reducing effective sizes. But then you can also adopt the air classification and also triboelectric separators for certain extent of the particle that you can target. But as an integrated module is not being quite straightforward attempted. I think the research has been carried for in isolation units. But I think now it's time, especially when you talk about a much cheaper beneficiation routes. I think this is still viable for some of the particles where there is a sufficient density and size differences there for the different mineral that you talk about, mineral as well as a gang particle that you see in the system. High rate and ceramic hyperbaric filtration. This is for dewatering. I think every process that we talk about, your energy again still limited if you try and reduce your cost of operation. So essentially, they get a different filtrations that you can target about it. This is on the basically we are talk about a process intensification to do the higher recoveries of the or separation of the moisture. Other things. Now we do also have a inline analytics and machine vision where predictive models that you can able to integrate with your process plant. So right now I think that's an era where we are moving a lot because there is a lot of data piled up, and then one can make a predictive model specific to that plant, um, and one can adapt. I think, see, I just want to take a minute here, digressing from the topic. Now today everybody is hyped for AI and ML. Now if you adopt those technologies, for example the mineral processing, or for that matter any process plant, what is a challenge we have it? Why we are not doing it outright? Okay. Mhm. Separation of what? Separation of. Okay. No, but see, now we are not talking completely kinetic driven processes. Vendor processing, even you do have without kinetic base, except flotation and grinding. Majority of them still you can go with the steady state assumption. All right. But why we are not adopting? What are in terms of the A and ML? What would be the stoppage for us to use completely? Hmm. Data availability, but I think now many plants are trying to generate that data, and also historical data is also there, they can able to place it. The main trouble for A and ML, let's say in the lab I have done a very controlled experiments, and you take about the first part, dry beneficiation. Let's say I have done the HPGR, air classifier, and also electrostatic separator, three of them integrated manner I have tried. Now I use, so I generated let's say hundreds of data, performance data, and I use the data analytics to get the model, and it predicts. Now it predicts very well for this, even less than 5% error. Now can I use this predictive model to do the upscale? So then upscale of A and ML again will be a problematic. So that means now A and ML is a specific for given process scale. So if it is a lab, it only works for the lab, and you cannot straight away take up for the upscale. Whereas if you go through the fundamental processes, for example, we talk about the grinding. The grinding rates, kinetics, whatever we try and do it with respect to breakage rates, they are the same when you talk about the scale up. So the fundamental, the difference between A and ML data analytics based driven model or predictive models are limited to that process. You cannot use and use for the upscale to predict it. Again, you need a new parameters fitting, provided you have a data available. So for upscale plants, let's say today we talk about the critical minerals, most of the plants are not available. They are only available in the laboratory. Now, if I use it, can I go and establish? No, I need to still generate at least some decent data to train my A and ML model to predict something. So the scale up is a major issue with this model. Whereas if you use a semi-empirical model, the lab scale to at least some decent scales that we have gone through conventionally, then those models still work very well within the range of slightly 10 to 20% error, whatever possible. So that is the drawback, but otherwise the data is a key. You need to have a data at every scale, then you can adapt for training. Hmm. Variability. You are talking about a feed. Yeah. So that's what I think the variables range what we use for even model predictions. They would be restricted. It's the same true for it is same for the even semi-empirical models also or mathematical models. The data is a limitation that we talk about it, but the upscale at least there is a possibility with that. But with the A and ML models, upscaling is completely not feasible unless you again regenerate some data and come back and fit it. The training of the data is most important part for it. Okay, so limited. That is also there. Yeah, right. So that I think that's what I'm probably I would say that data analytics or the A and ML now whatever we are trying to see as a hype today, which is there with the core engineering skills pretty long back, which are nothing but optimization. We do the optimization using genetic algorithms and ANN. Okay, but only the extra that they toasted with respect to imaging, which is again not straight away applicable for our systems. Probably mining, monitoring and management point of view, it is possible. For example, if you adopt the completely IoT, where you sit in the city and operate your plant, then you can adopt them because now you need to know what is happening in the shop floor at every stage. And then you try and see, and then the integration and sensors are the crucial. Until unless you get them working condition, then you cannot do anything. It's like the way we have seen the aeroplane crashes unknowingly what is the reason on it. So same here. So there are so I would say the ANML or data analytics today, whatever we are looking at, there is going to be certain limitation where we cannot replace the humans for every sector, especially in the mining and mineral. We still need a lot of manual interventions, particularly for even the feed variability that you just cited, which is quite possible. Now, until you generate that data, and for critical minerals is quite unimaginable right now. But you can still use it for predictive purpose at the feasibility point of view, but not as a plant scale. Plant scale, you need a data that you need to bring out. Okay, so then the geometrical geometallurgy as well as machine learning to be adopted for again a new resource that we see it. So I think this is what you can go for block modeling of a variability and dynamic routines, sorted outs for mill versus leaching or the separations that you can do it. But geometallurgical is the content that we have to do for every new source that we identify, because it is not the same uh, method that you can go for it. So I think with that is the main content, but otherwise, how much time we have it? So, okay. So see, I have the slides here, some of them, but I can just give you some basics in a way. What is needed for selecting, because majority of the separations are gravity-based separations. To enable the gravity separations, fundamentally what we need to check. So this is where we see that. So when you go by, the separation by the advantage of earth gravity, you can able to do it provided the particles can able to respond for the earth gravity acceleration. So that means now particle size should be coarse enough. If the size of the particle is small, you may not able to do it. And then for those particles, if they are not possible, then the second within the gravity separations, you have a both gravity separations and also centrifugal separation. So what you do is, instead of the gravitational force, you actually enhance the centrifugal forces, where your ratio compared to the earth gravity could be 100 times to 1000 times that you can go for whatever the separation. So for example, Nelson concentrated, we saw one of the gravity separation. So you will have about a 2 to 3000 range of the ratio of the acceleration compared to earth. So obviously you can make separations very fast. Okay, so that's the one route we need to do it, and it can work size wise, density wise. And moving on to flotation, we know that you need a air or the gas based on some of these properties. But then the hydrophobicity, or sorry, the selectivity towards the hydrophobicity behavior should be attempted. So I think if those behavior is being seen, you can apply for it. Then the magnetic, it's based on the magnetic susceptibility, whereas a leaching, again, which is down the line, we see that based on how they respond and precipitate with respect to different reactions subjected for selected reagents, you can apply for it. So this is in general a simple rule which we need to check it. But I think when you go for a detailed way for gravity separations, so these are the checks that we need to do before we subject. Otherwise, we cannot just close our eyes and say, now let us subject for gravity separation. There is no point if there is no density difference. So the gravity separation, if there is a certain density difference between the two mineral or the gangue or mineral, whatever, or rock the fragments, then you can able to separate by gravity or the dense media. These are the two methods that we go. And what is the density difference that we can go? So this is where dH minus dF, which is the your fluid that we use it, to the lighter component. So if you have two densities, and ensure the one is a lighter density and both of them should be above the fluid density. I think that is the criteria that we should go on it. Otherwise, it's very difficult. So if you go with the DD ratio and identify and find out what is this value. So these are the range of values that you can able to see. If the ratio of a DD is more than plus 2.5, then I think you can easily separate up to 100 microns using simple gravity separations. Okay, and this could be jigging, it could be even the spiraling, or even with the simple teeter bed separators. If it is between 1.75 to 2.5, the separation is possible, and you can do coarser size up to 150 micron. And if you go with the 1.5 to 1.75, it's very difficult to do down the 1.7 millimeter. So that means now for these things, you need to start adopting the centrifugal acceleration that you need to go on it. So if you have a less than 1.25, it is not possible. So I think these are the pre-checks that you have to have it, so that you can see whether any of this can be possible for separation through gravity, right? So the motion of the particle in fluid depends on not only the space gravity but also size. See, here we looked at the DD, but I think size also plays a role. So let's not forget about that. But otherwise, this is what we need to do. The efficiency of gravity separation therefore increases with the the particle size. If you go with the bigger size particle, gravity separation is quite easy. But then you need to ensure that that size is being represented by the feedstock that you send through. Okay. Particles which are so small that their movement is dominated mainly by surface friction responds relatively poorly for commercial high capacity gravity methods. In practice, close size control of feed to gravity separations is required in order to reduce the size effect and make the relative motion of the particle specific gravity dependent. So I think these are the few. I think mostly I will share the slides to you, but otherwise, yeah. So these are the variety type of them, and already we have seen what are those there. So dense medium. Anyway, we can do by normal gravity based if the size is quite large. If the size is too small, you can go for centrifugal separation based dense medium. Jigs also there, spirals. Spiraling is like now you allow the thin layer of the liquid and where the particle would actually experience centrifugal as well as a gravitational force together. And then the particle would segregate based on size and density across the trough. And then you can cut the particle of stream inner, middle, and outer based on your characteristics of whether you want to call it as one product and middling and rejects. I think all of them are also there. So the fine particle separator, Falcon MGS, we have seen, and then the gravity where hydrosizers that are needed. So I think I will skip the the jigs and other stuff. I think most important part that you need to know about the jigs and spirals also there. So again, spirals are quite good if the density difference is very high, about to go around. So the last I think is the fine particle side. These are the fine particle devices that you can able to see. So the Nelson, there are multiple designs within the Nelson. I think Nelson is again one of the scientists who invented this, and then I think it's Canadian-based company, and they produce this and heavily adopted for gold and also diamond. But you can also adopt for now critical minerals having higher density difference between the finer size particle. You can go up to 10 micron range of particle separation by this route. And So the difference compared to other thing is the capacity. So you can see now they actually subject very high speed centrifugal acceleration. Then the particles of a valuable one higher densities would actually get filled in the chamber. Lighter one actually will go away as a uh, tailings. Now once it is done, then all the chamber is filled. You can actually stop the machine and collect your product separately as a separate route. So that is there for Nelson separator. And Falcon is also similar one, but I think here Falcon you also get automated collections that you can able to do concentrate, middlings, and tailings, and three products that you can able to get from this. And again, centrifugal you can also see different units that are available. But I think for so this slide probably you should remember that what is the range of sizes that you want to use it, and particle size, because density we know the DD ratio, but size is also very important. And up to flotation we can go up to close to a micron or 10 micron range flotation. But I think now if you go with the solvent rate, you can do up to almost down the line any size that you can go. And then I have this MGS, but I think this is only available at research mode. It is not being practiced in the commercial scale, so I think I will skip it. Hydrosizer is the one which you can actually do it two ways. One is utilizing the fluidation route, having a particles of a multi-density, you can actually separate those particles at the different elevations. So latest technology on that is a reflex classifier. Okay, this is from Australia, University of Newcastle. And what they do is, I think both are similar. If I look at the hydrosizer, what we do in hydrosizer, that we actually take a feed from the top, we create the fluidization using the water, right? You can see now water we use fluidizing the particle. When you fluidize, each particle now subjected for its free settling condition. Now bigger one, heavier one, like you can see heavier one would come as a first product, and you can collect them this thing. And then the water velocity, the way you operate is such a way that you can actually take out the certain size and density along with it with respect to if you know the terminal velocity of those particles. So you operate the velocity of the water higher than the target size of the particle that you want to separate it, and those particles will go along with the water, and the heavy settling velocity particle, they will come down as a product. But this is in the simple vertical fluidization. Now the next concept, that the way they have done it, can we see when you are going by this, what uh, uh, it is being understood that some of the finer particle are being trapped along with the water and bigger size particle. Now they are unable to retract that particle back into if the heavy but smaller size particle supposed to come down, but that is going away. So then they say that can we now create a lamella flow? So that means now you create a inclined channels. Now when you have an inclined channel, what happens? Up to here fluidization is happening. Now whatever the separation of a heavier one would be done, coarse and heavier one already done. But what about if heavy particle but small in size might be getting trapped along with the other size particle? Now if you have a inclined channels, what they see that there is a capillary action for the particle, where some of the particle, if they are flowing in the laminar flow condition, they can able to get a chance to come back from the trap or entrapped condition, and then they will come back. So that technology is being proven well for very fine particle separations as of now. And of course you have to, for every unit that you plan for adapting for plant, you have to have a feasibility assessment and performance guarantee first and do it. But otherwise this is the one which even in the initial slides for critical minerals also being quite adaptable, especially if you have a very fine particles of close, so narrow density, but then you have a size variation slightly, that you can able to do it. But if the density difference is there, then you choose the gravity separation like Nelson and Falcon, and that too for fine particle. But if they are nearby with the same density, you may not be able to do with that, and these are the units that you can target to do. Yeah, I think that's what I wanted. But otherwise mineral processing, advanced mineral processing course I run for full semester, okay, which is there in the next semester typically. So I cut a lot to make it as a 2.5 hours slide. So I think so the basics of this probably I can share the slides to you. so that you can go through whenever you have a convenient time to look at it. All right. Any questions you have, clarifications that you want to sort it? Yeah. Hmm. Yes. No, no. So it's a hydrocyclone first. When you say hydrocyclone, so look at the flotation. In flotation, there is simple counter current flow where the solid particle from the top comes and then you have a bubbles that are being generated and they go and have a contact and you get it. And if you use a mechanical flotation, you are trying to induce some local current so that you also try and bring the bubble and particle together. But now in case of cyclone based air spots flotation, what they do is if I have a fine particle, some of the fines may not be able to get contact with the bubble at all because they take the water path line. And if we create a eddy currents, the eddy currents would control the trajectory of the fine particle and they never got closer to bubble at all because there is a density difference between bubble and particle, right? Obviously, bubble would not come closer at all. So then in that case, what they say is that can we now enhance the particle segregation instead of closer to the impeller, little away from the impeller. That means now you can able to do if you take a hydrocyclone, what happens? When you subject for tangential force for the particle, now particles very coarse will be on the wall, but very small towards the middle, right? Just close to the central air core. Now you are actually making the fine particle to come to the central column rather than just taking a path of the water all the way. Now when they are and also under high centrifugal force. Now particles are in a equilibrium form, very fine, next size, intermediate and very coarse. They are there. Now you introduce the air from the sides of the hydrocyclone. So it's air spots through walls, not at the entire column, but I think some range of the middle to bottom. So that now these bubbles, what happen? Now bubbles in the centrifugal action, what happen? They also be very density difference wise very small. They try and come to the center zone. The air in the centrifugal action, air bubbles, if the bubble size is too small, they also come to the central zone and they come and try to disperse the merge with the air column if it is available. But some of them they are taking so if you look at the trajectory of the bubbles, let's say from this wall, I think I can write it better on this. So you assume this is the wall. Now you have created this is a central air core, right? This is air core that is there, and you have a smaller size particle and intermediate, and then slowly you have a bigger size particle that are there. So if the air is being induced from here, for example, I am looking at only some zone. Now air bubbles, they are supposed to go and because their density is very less compared to even bubble particle. Now they would come and definitely they would take a path towards the air core zone. So then when they are moving, actually we can expect the better contact between finer particle to bubbles, and they say that actually enhances the separation for finest particle size that are possible in that manner. But it is research exploration still going on, and Chinese, I think, I mean, we had to really salute them the way they speed up the activities. Okay. In fact, I read an article, I think this was just there, it's a Hindu article. The way the critical minerals production that they are doing, they are not doing through automated versions all the way. So they give a contract for one of the agency, and these agencies, they establish like a smelter if you want to do it, right? They don't go for big smelters like the way our domestic silver and the gold they prepare, right? It's like a small furnace that they will have. Now this contractor brings a lot of skilled labor to do this, and then he produces the quantity that is targeted to give as a part of the contract. So that means if you try and look at their technology, it's not a very hi-fi technology, but I think it's a precise time-bounded targets that they go on deliver it. And I saw one of the floor, they were showing that small furnaces, the way we make domestic silver and gold ornaments out of it, they were making the required target of the volume and then generate. So every day they have the target to give. Whereas here we try and see that how do I make this as a large scale production. By the time 10 years gone, we get. So I think that is where the skilled labor, probably India, China can able to do better compared to the rest of the world on this matter. Yeah, I mean that's our strength. Probably we should utilize in better off on those things. But anyway, so that's a air spudge flotation where you can target finer particle to have a definite contact with the bubble when they are coming radially migrating to the central zone. And at the end, the bubble goes and merges with the, I mean, not the merges, but the nearby zone, and then they float on the top of it. Hmm. No, froth camera is the top view. Mm, top view, right? Once you get a froth collected on the top, so I think there is a separate research is going on at a Imperial College as well as I think at a Imperial, where see if you look at the soap froth that we use for the detergents washing cloth, right? You get a very nice froth. What is this froth all about it? It's actually air bubbles and you have a water contact between them, right? Now, if you try and look at the top view, the froth that comes on the top will have a largest size possible, stable size, largest stable size. If the stability is not there, it bursts out, right? Now, when you try and look at it, so one can also see that when I am getting the particles carried by the bubbles up to top surface, and then the immediate reach bubble would actually merge with the froth immediately, right? If it is stable enough, otherwise it's collapse. So assuming all the bubbles that are reached on the top, I mean the interface of the froth would be stable enough, but that froth doesn't stay as it is. Immediately it coalesces with the other bubbles that are there. So essentially it forms the maximum size of the bubble the moment it comes before surface pressure, whatever that is there. So what is froth camera look at it? What is the effective size of the bubble I am getting? Now once I know the surface of the bubble or bubble size, I can estimate the surface area. What is the surface area is contained? Floated particle with it. So then I would know what is the mass concentration of the particle that are coming. Yeah, otherwise what you have to do is you need to ensure this entire froth gets collected and then you need to look at after downstream process how much it is. But the for main problem for all this froth that goes, very difficult to measure the mass flow rate of the bubbly froth. You cannot calculate how much of the solids are there with that. But by imaging, you can able to calculate what is my projected area of the bubble, and then from there you can estimate what is the maximum concentration that is possible, and then give an indication that will be as an input for you to operate the other dynamics. For example, you are in the research side, laboratory research side, you realize that if I get about a 10 bubble froth, it's going to have a maximum collection. Now, if that is not coming, and then as operator, we know that something is not effective that is happening. So then immediately it goes as a controller to go and say, can you increase the bubble, the flow rate, air flow rate, or other condition that. So it's like an indicator for looking at the maximum stable bubble, and through that you can calculate what is the maximum collection that might be possible. Yeah. Right. Any other questions? Yeah, I guess afternoon we can go to the lab. So I think we plan the mineral processing lab visit. So I think you have to be there, both of you and Anikara. So we can start with the first sample preparation lab, MUO lab. Okay, you can inform Nagarjuna to be there by 2:30. I think we can hopefully go there by 2:30, 2:35. And then first observe, I mean, because some of them, they need to see how we are actually doing at a laboratory level. And then come to the ground floor. So after that, I think maybe MPAs we can, because most of the critical minerals, what we talk about it, the assay basis. How do we do the assay, all that? I think we have also one of the tutorial down the line next week. Dr. Sai Pranith, who is expert on assay measurements of these critical minerals, especially rare earths. He can able to suggest you step by step how to do the standardization of these reagents that you use for your ICP OAS or ICP or MPAS. So I think that's a worthy, even if I ask me, I also need to learn those things effectively, because we don't practice all the time. We rely on the students to pick up and start the story. So I think it's going to be some interesting, and also isomel is there in the lab. We can also look at it. I'll try and contact if possible for atom probe check with one of the faculty. He said he's available in the afternoon, but I had to call him and check. Okay. Yeah. All right. So hopefully we can engage in the lab. See, a lot of things we can do, but as a part of tutorial, it's like we are seeing participants with a different background. It's not quite sensible again to go back and do the basic mass energy balances, all that. I think I'll leave that aside as part of this course. Okay. All right.